Imagine a force so vast and invisible that it makes up nearly 70% of everything in the cosmos. Yet it cannot be touched, seen, or fully explained. Without it, galaxies would not drift apart as they do. The night sky would look unimaginably different, and the fate of the universe itself might already be sealed. This is dark energy, the most elusive substance in all of cosmology, and today we dive into the breakthroughs that may finally begin to reveal its secrets. Scientists say dark energy accounts for 68% of the universe's total energy budget, and yet they cannot tell you exactly what it is. How can a force so dominant remain so mysterious? That question opens one of the greatest scientific puzzles of our time, and its answer could redefine our understanding of existence itself. Before we unravel the discoveries, here is a reminder that knowledge of this scale changes the way we see our place in the cosmos. To stay on this journey into the unknown, subscribe, like, and turn on notifications so you never miss the revelations shaping the future of science. The story begins with a shock from the late 1990s. Astronomers observing distant exploding stars, supernovae, expected to confirm that gravity was slowing the universe's expansion. Instead, they found the opposite. The galaxies were accelerating away, as if some hidden force were pushing space itself outward. Imagine tossing a ball upward and expecting it to slow, only to see it speed up and fly off into the sky forever. This discovery stunned the scientific world and earned the 2011 Nobel Prize in Physics. The name given to this invisible push was dark energy. Yet naming it solved nothing. It only deepened the mystery. What could possibly power such cosmic acceleration? Since then, dark energy has become the defining enigma of cosmology. To grasp its scale, picture this. If matter were the only ingredient of the cosmos, then galaxies would slow and eventually collapse inward under gravity. Instead, the opposite happens. The acceleration is so dramatic that in 100 billion years, distant galaxies will recede so far and so fast that their light will never reach us again. The universe would appear empty except for our own cluster of galaxies, a lonely island adrift in an invisible ocean of expansion. That is the kind of future dark energy points toward. But what is driving it? Scientists propose several ideas, each stranger than the last. One possibility is the cosmological constant, first introduced by Albert Einstein in 1917. He imagined space itself might possess an intrinsic energy that resists gravity. Later he called it his biggest blunder, but it may in fact be true. In this view, every cubic centimeter of empty space contains a fixed amount of energy, endlessly stretching the cosmos. Another theory is quintessence, a sort of cosmic field that ebbs and flows like a tide, growing stronger or weaker over time. If quintessence exists, expansion could eventually slow, stop, or even reverse. Still others suggest dark energy could be a sign that Einstein's theory of gravity is incomplete, hinting at a new physics beyond what we know. Each possibility carries profound consequences for the fate of everything. To test these theories, scientists have built some of the most ambitious experiments in human history. Projects like the Dark Energy Survey scanned over 300 million galaxies, using one of the most powerful cameras ever constructed. From 2013 to 2019, it mapped the cosmic web of matter, measuring how galaxies clump together and how expansion bends their light. In 2023, results indicated subtle deviations from predictions, raising the possibility that our models may not fully capture dark energy's role. Meanwhile, the European Space Agency's Euclid telescope, launched in 2023, is now mapping billions of galaxies with breathtaking detail. Its mission: to chart the geometry of the universe and determine whether dark energy behaves like a constant or a shifting field. NASA's Roman Space Telescope, scheduled for launch in the late 2020s, will expand this quest by studying supernovae across vast cosmic distances. Each of these missions is a colossal step towards solving the puzzle. Consider the scale of these surveys. Euclid will cover an area of sky equivalent to 1/3 of the entire night dome, capturing light from galaxies billions of light-years away. If printed, its data would stack into a tower taller than Mount Everest. That is the level of measurement required to probe a force that cannot be seen directly. And yet, even with such precision, dark energy continues to defy simple explanation. The data often matches multiple interpretations, leaving scientists to peel back layers of ambiguity one observation at a time. But recent breakthroughs are beginning to tip the balance. In 2024, analysis of baryon acoustic oscillations, ripples from ancient sound waves frozen into the distribution of galaxies, provided fresh evidence that dark energy behaves very close to a constant. Think of it like ripples in a pond that froze in place billions of years ago, ripples we can still measure today. These patterns act like cosmic yardsticks, letting scientists measure expansion across billions of years. According to results from the Sloan Digital Sky Survey, dark energy's influence has remained steady over much of cosmic history. That consistency favors Einstein's cosmological constant, though small uncertainties remain that could keep other theories in play. At the same time, particle physicists have run into a paradox known as the cosmological constant problem. If vacuum energy arises from quantum fluctuations, then the amount should be 120 orders of magnitude larger than what astronomers observe. That's a number so absurdly off that it has been called the worst prediction in science. How can the quantum vacuum predict a universe so violently unstable, while observations show a gentle acceleration instead? Some suggest hidden symmetries cancel out most of the vacuum energy, leaving only the faint residue we see. Others propose we live in a multiverse, and only in regions where dark energy is small can galaxies and life exist. In that sense, our very existence might be evidence of a cosmic selection effect. The stakes rise when we consider the future. If dark energy is constant, the universe will accelerate forever, growing colder and more desolate with time. Stars will burn out, galaxies will fade, and the cosmos will head toward a heat death. But if dark energy strengthens, it could trigger a big rip, tearing apart galaxies, stars, and even atoms in tens of billions of years. If it weakens or reverses, expansion could halt, leading to a collapse known as the Big Crunch. Our ultimate fate depends on what dark energy truly is. Every new measurement tightens the boundaries of these scenarios. This is why dark energy breakthroughs matter not just for theory, but for human perspective. To think that 70% of reality is hidden, influencing everything, yet invisible to our instruments, challenges our very notion of knowledge. It reminds us that what we see is only a sliver of truth, and the cosmos may hold deeper mysteries than we can imagine. To keep exploring them together, make sure you subscribe, like, and turn on notifications, so you stay with us as we unlock the greatest secrets of the universe. Curiosity spikes appear everywhere in this story. For instance, what if dark energy is not energy at all, but evidence that gravity itself works differently on cosmic scales than it does locally? Imagine if Einstein's equations are like a map that works perfectly in one city, but breaks down when you try to chart the entire world. Modified gravity theories propose exactly that. If proven true, this would revolutionize physics on a scale not seen since relativity itself. Testing such radical ideas requires exquisite precision, comparing galaxy clustering patterns to predictions, and searching for deviations that reveal new laws. Already, some discrepancies between cosmic surveys and predictions hint that modified gravity may not be out of the question. Another frontier lies in combining different types of observations. By pairing gravitational wave astronomy with cosmic surveys, scientists can cross-check the expansion rate in independent ways. For example, when neutron stars collide, they emit both light and gravitational waves. By measuring the distance from gravitational waves and comparing it to the redshift from light, researchers obtain a standard siren measurement of cosmic expansion. As detections grow in the coming decade, they may provide fresh insights into dark energy's role. Imagine listening to the universe's deepest rumbles and using them to weigh the strength of a force we cannot see. Dark energy even intersects with particle physics in surprising ways. Some models suggest it could be linked to hypothetical ultralight particles or invisible fields. Experiments with atom interferometers and precision measurements might catch faint traces of such fields here on Earth. Although these effects would be minuscule, perhaps changing energy levels by less than a trillionth of a percent, they could hint at connections between cosmology and quantum theory. The fact that researchers are chasing both cosmic-scale signals and subatomic whispers underscores how all of physics now converges on this enigma. So, where do we stand today? After 25 years of searching, dark energy remains unsolved, but each breakthrough narrows the possibilities. The latest surveys suggest it behaves like a cosmological constant, steady and unchanging. Yet unexplained tensions like the differing measurements of Hubble's constant, the current expansion rate of the universe, hint there may be more to the story. If these tensions persist, they could be the first cracks in the wall, clues pointing toward a deeper truth. Perhaps dark energy is not a single phenomenon but a symptom of something grander, like hidden dimensions or new interactions. The mystery deepens even as we approach the light. As we conclude, remember that every galaxy in the sky is carried outward by dark energy's invisible tide. When you look up, you are witnessing the consequence of a force that permeates all of reality. To understand it is to understand the destiny of the cosmos itself. That pursuit is one of humanity's most daring endeavors, and you are now part of that journey. Subscribe, like, and turn on notifications to keep exploring with us as the universe slowly reveals its most profound secrets. This is Tech Mythos.